Do you like weed? Well, we don't, so we're here to introduce you to the weed.
Wacker. Weed Whacker's purpose is to cut grass, ground cover, and of course, weed.
Our group is Kirby Sword, and we're gonna get into the weeds about how this thing works.
This is the general system of what we will be talking about. Notice where the fluid flows into the carburetor, through the cylinder, and out of the intake. Let's take a closer look at the carburetor.
First, fuel gets sucked into the carburetor from the fuel tank. Next, the fuel will exit from the exit hole, then travels along the diaphragm into the pool. From the pool, the fuel will travel through the filter hole. From the filter hole, the fuel will collect into the lower reservoir. Side note, as the fuel flows through the passages of the carburetor, we can assume minimal viscous losses because the corners are curved to help prevent separation from happening. Lastly, this is where the fuel will be sucked into the intake chamber where it mixes with air.
When the ripcord is pulled, the crankshaft will move the piston up and down. This will suck in the air, which later mixes with the fuel. After a certain amount of fuel is sucked into the combustion chamber, the energy added by the spark plug will combust the air and fuel. This will power the piston and in turn will be able to suck more air and fuel by itself to sustain a cycle. In order to take a closer look at the fan, one thing to notice is that this piece is made of aluminum, making it an ideal conductor of heat. The manner in which the fan spins matters, as the pocketed features mirror the function of a radial flow pump, where the fluid of interest is hot air. As the piston assembly functions, part of the generated heat will travel down the connecting rod through the crankshaft and into the fan. In essence, the fan will then dissipate heat into the surrounding fluid in two ways. First, it will act as a spinning heat sink, using conduction to remove heat from the combustion assembly, and secondly, the fan will cool off the system via convection with the nearby room temperature air.
Wacker is designed this way to replace the use of shears, allowing people to reach difficult places with high efficiency. Since it is a handheld device, enlarging the entire device would damage its purpose. However, different sizes can be beneficial for different individual parts.
One example is adjusting the displacement capacity in a cylinder. By expanding the volume of air to compress with respect to the piston's travel distance, more power could be generated by the system. Another way to boost power is to raise the ideal compression ratio to 13:1 or above, considering this engine runs on high-octane gasoline. And yet, there's a reason why these two changes are not implemented by the manufacturer. The Weed Whacker needs to be small and easily maneuverable, and thus a larger engine might give it more power, but it will also consume a lot more fuel and it would make it more cumbersome to handle. Another example is that one needs to be mindful to avoid changing the length of the intake too much. As is, it's a straight pipe to the filter and that's all. However, on more complex packaging, a winding tube can make it significantly difficult for the piston to have enough power to suck in the right amount of air.
One last example is if we change the height of the idle speed adjusting screw located on the carburetor, and how the amount the throttle valve can close varies. If there's not enough air flowing through the two tiny holes located on the disc of the throttle valve, then to supply more air during idle, one can lower the idle speed adjusting screw such that there is a slight gap between the side of the disc and housing. It is useful to adjust the screw depending on the air-to-fuel ratio within the carburetor. If there is too much fuel being used, this is inefficient and harmful to the system, so lowering the screw would force the throttle valve slightly open to enable more air to get into the mixture.
Now let's look at the equations and concepts when analyzing the Weed Whacker. First, the Bernoulli equations allow us to calculate irrotational flow throughout the system and to pressurize it in order to transform fuel into kinetic energy through pressure differences. The venturi within the carburetor causes a reduction in the area of the chamber before it is expanded once more through the exit. Since we assume that the fluid flow is incompressible, we can apply this change in area to Bernoulli's equation due to pressure differences.
Since the area is reduced at the throat of the venturi, the flow will have an increase in velocity, which in turn increases the dynamic pressure. However, in order for the Bernoulli's equation to be valid, the total pressure at the inlet must be equal to the total pressure at the throat. Therefore, the static pressure must decrease at the throat. As the fluid flows out of the venturi where the area of exit is greater, the velocity decreases, so dynamic pressure decreases. But static pressure must increase for Bernoulli to apply. Using the Reynolds equation, we can find that the fluid flowing through the venturi has a Reynolds number greater than 13,000, meaning it's turbulent. This makes sense because two fluids are essentially being mixed, causing turbulence in the fluid flow, and with the geometry of the carburetor, the two tubes connecting the fuel reservoir will automatically pull in at the correct stoichiometric ratio the fuel into the air, mixing both of them regardless of the velocity of the air being sucked through the intake.
Lastly, to demonstrate how fluid flows through the system, we will pour water into the carburetor. We can see water flow from the valve, out the exit hole, and shortcut into the filter hole, just as described through our CAD.